This is an integrative exercise from page 148 in the textbook. We're taking information from this chapter dealing with concentrations, dealing with writing equations for precipitation reactions, and we're combining that with information from the last couple chapters with limiting reactants, theoretical yields, general stoichiometric calculations. So the first piece of this problem asks us to write out a molecular equation for this reaction. In order to write out an equation, we really want to think about what compounds we have. So first thing we want to figure out is what ions we have. So potassium phosphate, potassium is K+, phosphate PO4, 3 negative. Then we've got silver nitrate, where silver is Ag with a positive charge, and nitrate is NO3 with a negative charge. So we know that the first thing we're starting with is 70.5 milligrams, so that means we've got solid potassium phosphate, and we write potassium phosphate as K3PO4. And we can tell that that's going to be a solid, again, because they're telling us that we start in milligrams, and I know that it takes 3 potassiums to balance the charge on 1 phosphate. Next thing we're reacting that with is silver nitrate. That formula is going to be AgNO3. And I know it's aqueous because they gave me a concentration, so that means I have a solution, moles dissolved in some liter. The products, we're going to figure out how everyone switches partners. So the potassium is now going to be with the nitrate, the silver is going to be with the phosphate. So my first product is going to be KNO3 because those charges cancel. If I think about my solubility rules, I know that nitrates are always soluble, so this is going to be aqueous, which means that my next product, the Ag3PO4, must be my solid. And if you look at your solubility guidelines, you'll see that that must be our precipitate. The last thing we want to do for this is make sure it's balanced. So since I see 3 silver atoms on the product side, I want to make sure that I have 3 on the reactant side. That is also going to give me 3 nitrate groups. So I want to make sure I also have 3 nitrates on the product side, and that's good because that balances my potassium. So I've got 3 potassium atoms on the product side and the reactant side. All right, that takes care of part A. Part B wants us to figure out the limiting reactant. In order to figure out limiting reactants, I like to use the ice tables, where the I is initial, C is change, and E is the end. So getting that table set up, remember we divide it for each of the substances. Okay, so the initial amounts we need to figure out. Remember that we can only put moles into this ice table, so we're going to convert everything we know into moles. They're telling us that we start with 70.5 milligrams of potassium phosphate, so putting that into regular grams, that would be 70.5 times 10 to the negative third grams of K3PO4. If I want to know moles, I'm going to need to find the molar mass. That's going to be from the periodic table. So I'm going to add together the mass of 3 potassium atoms, 1 phosphorus, and 4 oxygens. And that way I'll know that 1 mole of K3PO4 weighs 212.3 grams, which means I'm going to have 3.32 times 10 to the negative 4th moles of potassium phosphate. So that can go in the first box of my ice table. Okay, I want to do the same thing for the silver nitrate. I want to figure out how many moles I have. This time they don't give me grams to start with, but they do give me a volume and a concentration, so I can use that to solve for moles. Changing the milliliters into liters, I know that I've got 0.015 liters. I know that there are 0.050 moles of the silver nitrate in every liter. Again, that's just the concentration expressed in units of moles per liter. So doing that math, that means I've got 7.5 times 10 to the negative 4 moles of silver nitrate. Notice that I've only got 2 significant figures here. That's because both of the pieces of information I'm using only had 2 significant figures. I know that I don't start with any moles of the products. Remember that the change row has to do with the coefficients. So this is going to be minus x because I consume it. This is going to be minus 3x because I consume it 3 times as fast. This is going to be plus 3x because I produce it at 3 times the rate that I produce the other product. Remembering this dividing line here, the reactants always have negative signs because I consume them. Products have positive signs because I'm producing them. So what we can do is we can try to figure out what we're going to run out of first. You can either solve for x to figure out which x is smaller, or just eyeball it. In this case, it's pretty straightforward to eyeball it. If you look, we've got about twice as much of the silver nitrate as we do with potassium phosphate, but we consume it 3 times as fast. So since I only have twice as much, but I'm consuming it 3 times as fast, that means that I'm going to run out of the silver nitrate first. So that's going to end in 0 because I completely consume it. And when I solve for x, x is going to be equal to 2.5 times 10 to the negative 4 moles. So I can go ahead and do the math in order to figure out the end for the other boxes. This is going to be 3.32 times 10 to the negative 4 minus 2.5 times 10 to the negative 4. So the final answer for that is going to be 8.2 times 10 to the negative 5 moles. 3 times x in here gives me a final answer of 7.5 times 10 to the negative 4 moles, and plus x here just means that this is 2.5 times 10 to the negative 4 moles. Okay, so this already took care of our answer to part B. We know that the limiting reactant in this case was the silver nitrate. And we are ready to do part C, calculating the theoretical yield in grams of the precipitate that forms. So we already know how much of the precipitate we have in moles, so now it's just a matter of taking the moles of the precipitate, remembering that the precipitate's the solid, and converting that into grams. So 2.5 times 10 to the negative 4 moles Ag3PO4. Using the periodic table, you can find that the molar mass of this is 418.7 grams. So doing that calculation and rounding it to only 2 significant figures, we're going to get 0.10 grams. So we have a total of this many grams Ag3PO4. So again, this is an integrative exercise because it combines concepts we've learned from the previous 2 chapters. This is something you really want to make sure you're comfortable doing because it's possible that you could have a test question that asks you to do this. Taking what we know about precipitation reactions, what we know about using molarity to do calculations, combining that with what you know about limiting reactants.